Hello, this is Kwang. In this video, I'd like to walk you through all the existing nodes I have proposed for our deep learning map on One Academy. So let's start with the first node here. Deep learning is a particular kind of machine learning that achieves great power and flexibility by representing the world as a nested hierarchy of concepts, with each concept defined in relation to simpler concepts and more abstract representations computed in terms of less abstract ones. Okay, so deep learning algorithms. Deep learning algorithms can be implemented to solve real-world problems today. And deep feedforward networks, also called multi-layer perceptrons, as the quintessential deep learning model that is behind nearly all modern practical applications of deep learning. And scaling these models to large inputs such as high-resolution images or long temporal sequence requires specialization. The first example is the convolutional neural network, CNN, which can be used for processing large images. And another example is the recurrent neural network, RNN, which can be used for processing temporal sequences. So then I will first introduce the feedforward neural network to you. Okay. Deep feedforward networks, also called feedforward neural networks or multi-layer perceptrons, are the quintessential deep learning models. It was the first and simplest type of artificial neural network devised. In this network, the information moves in only one direction, forward from the input nodes through the hidden nodes, if any, and to the output nodes. There are no cycles or loops in the network. The goal of a feedforward network is to approximate some function f star, for example, for a classifier, which maps an input x to a category y. A feedforward network defines a mapping y equal to f of x theta and learns the value of the parameter theta that result in the best function approximation. So next, I will show you the overall structure of a deep forward network. Feedforward neural networks are called networks because they are typically presented by composing together many different functions. The model is associated with a directed acyclic graph describing how the functions are composed together. For example, we might have three functions f1, 2, and 3 connected in a chain to form this equation, and the chain structures are the most commonly used structures of neural networks. So I will introduce the layers of neural network to you. In this specific example here, F1 is called the first layer of the network, and F2 is called the second layer, and so on. The final layer of a feedforward network is called the output layer. During neural network training, we drive fx to match f star x. The training data provides us with noisy approximate examples of f star of x evaluated at different training points. Each example x is accompanied by a label y. The training examples specify directly that the output layer must produce a value that is close to y at each point x. However, the behavior of the other layers is not directly specified by the training data. The training data do not say what each individual layer should do. Instead, The learning algorithm must decide how to use these layers to best implement an approximation of f star. Because the training data does not show the desired output for each of these layers, they are called hidden layers. And you can see in the graph here, this is a simple neural network with only one hidden layer. Okay, so next is the connection between layers of neural network. In the chain structure of a feedforward network, let's assume the input example is x, which is a vector of dimension d, and it will be the input to the first layer. As you can see in the first equation here, we will first apply a weight matrix W1 to x and then plus a bias vector b. And then an activation function G1 will be applied on the output and we will get H1. And then H1 will be the input to the next layer, the second layer. And similarly, in each layer, you will first apply a weight matrix W on the input and then plus the bias vector B and then apply an activation function G to get the output. The output of the previous layer will be the input to the next layer. And here is a graph that shows how the information flows in the neural network. And next, I will introduce what is the activation functions and how is their roles. What is the role that they play in the neural network? So, activation functions are mathematical equations that determine the output of a neural network. The function is attached to each neuron in the network and determines whether it should be activated or not, based on whether each neuron's input is relevant for the model's prediction. Activation functions also help normalize the output of each neuron to a range between 0 and 1 or between -1 and 1. So, the role of the activation functions in neural networks. As we have introduced in a neural network, numeric data points called inputs are fed into the neurons in the input layer. Each neuron has a weight, and multiplying the input number with the weight gives the output of the neuron, which is transferred to the next layer. The activation function is a mathematical gate in between the input feeding the current neuron and its output going to the next layer. It can be as simple as a step function that turns the neuron output on and off, depending on a rule or threshold, or it can be a transformation that maps the input signals into output signals that are needed for the neural network to function. There are a lot of types of the activation functions. So generally, there are three types of functions. The first is binary step function, and then linear activation function, and nonlinear activation functions. So let's start with the binary step function. As you can see from the figure here, a binary step function is a threshold-based activation function. If the input value is above or below a certain threshold, the neuron is activated and sends exactly the same signal to the next layer. And in this specific example shown in the graph, you can see that the threshold is set to be 0 here and if the input value is above 0, then it will output 1.02. And these values can be tuned by the users as they want. So next is the linear activation function. As you can see here, it takes the input multiplied by the weights for each neuron and creates an output signal proportional to the input. In one sense, a linear function is better than a step function because it allows multiple outputs, not just yes and no. And we will move on to the nonlinear activation functions. Modern neural network models use nonlinear activation functions. They allow the model to create complex mappings between the neural network's inputs and outputs, which are essential for learning and modeling complex data, such as image, video, audio, and datasets, which are nonlinear or have high dimensionality. There are 7 common nonlinear activation functions, and then we will introduce each of them to you. So we will start with the sigmoid. Okay, it's here. Oh, oops. Okay. So you can see here is the sigmoid function, and here are the pros and cons of this activation function. The pros are that it has smooth gradients, which can prevent jumps in output values, and the output values bound between 0 and 1, which can normalize in the output of each neuron, and the clear predictions for x above 2 or below -2 tends to bring the y value to the edge of the curve, very close to 1 or 0, and this enables clear predictions. And the cons of the function are: the first is vanishing gradient. For very high or very low values of x, there is almost no change to the prediction, causing a vanishing gradient problem. This can result in the network refusing to learn further or being too slow to reach an accurate prediction. And also, the outputs of the function are not zero-centered, since it is centered on 0.5, and it is computationally expensive. Okay, so next will be the hyperbolic tangent function. Okay, you can see that this function is zero-centered, so making it easier to model inputs that have strongly negative, neutral, and strongly positive values. And also, it has smooth gradient. The output values are bound between -1 and 1, normalizing the output of each neuron, and also clear predictions. And for the cons, like the sigmoid function we just introduced, it has the vanishing gradient problem, and it is computationally expensive. Next, I would like to start with the ReLU function, rectified linear unit. Okay. Okay. So as you can see here, the pros of ReLU are that it is computationally efficient and allows the network to converge very quickly, and it is nonlinear. Although it looks like a linear function, ReLU has a derivative function and allows for backpropagation. And the cons of this activation function is that it's the dying ReLU problem. When inputs approach zero or are negative, the gradient of the function becomes zero. The network cannot perform backpropagation and cannot learn. And then I will introduce a couple of uh, functions that are special ReLU functions. So the first would be the Leakley ReLU. As you can see here, this variation of ReLU has a small positive slope in the negative area, so it does enable backpropagation even for negative input values, and this prevents the dying ReLU problem. And also it is computationally efficient and it is nonlinear. And the cons of this activation function is that the results are not consistent. Leakley ReLU does not provide consistent predictions for negative input values. Oops. Okay, so the next one would be parametric ReLU. Okay, as you can see from the graph, this activation function allows the negative slope to be learned, unlike Leakley ReLU. This function provides the slope of the negative part of the function as an argument. Therefore, it is possible to perform backpropagation and learn the most appropriate value of alpha. And the other pros are just like the ReLU, and the cons is that the function may perform differently for different problems. And here is the switch function. You can see that the switch function is a mathematical function defined as follows, where beta is either constant or a trainable parameter depending on the model. And for beta equal to 1, the function becomes equivalent to the sigmoid-weighted linear unit function used in reinforcement learning. Whereas for beta equal to 0, the function turns into the scaled linear function fx equal to x over 2, and with beta tend to infinity, the sigmoid component approaches a 0-1 function, so switch becomes like the ReLU function. Thus, it can be viewed as a smoothing function which nonlinearly interpolates between a linear and the ReLU function. And here is the last activation function, the softmax function. It is defined by the formula here, And in words, we apply the standard exponential function to each element Zi of the input vector Z, and normalize these values by dividing by the sum of all these exponentials. This normalization ensures that the sum of the components of the output vector sigma Z is 1. And the pros of this function is that it is able to handle multiple classes only, And in other activation functions I have introduced, there is only one class. So this function is special because it can handle multiple classes. It normalizes the outputs for each class between 0 and 1 and divides by their sum, giving the probability of the input value being in a specific class. And also it is useful for output neurons. Typically, softmax is used only for the output layer. For neural networks that need to classify inputs into multiple categories. So that is all the activations I'd like to introduce here. And let's come back to this node. As you can see, in each layer there is an activation function applied. I'd like to make a comment here is that for all the layers except for the output layer, the activation functions will generally be the same type, while the activation function for the output layer will be a different type. And how to choose the activation function for output layer depends on what kind of classification you'd like to make. For example, if that is multi-class, then softmax function would be a good choice. While for what functions to choose for the previous layers, that could be a more difficult question, and there is no specific answers to the question. And a possible direction for the new nodes in our deep learning map is to add the nodes to explain which activation function is preferred in what kind of circumstance. Okay, so that's all for the overall structure of the neural network part. And in case of that, the links in the map may cross and it may be a little bit messy. I will hide the nodes I have introduced, and then we will move on to the next part. It may take some time. Okay, great. So next we'll move on to the stages of neural network learning. Generally speaking, neural network or deep learning model training occurs in 6 stages. That is initialization, forward propagation, arrow function, back propagation, wait, update, and iterate until convergence. At the end of this process, the model is ready to make predictions for unknown input data. New data can be fed to the model, a forward pass is performed, and the model generates its prediction. So next, I will introduce each of the stages to you. So let's start with the first one, weight initialization. So at the beginning of a neural network training, initial weights are applied to all the neurons. It is necessary to set initial weights for the first forward pass. Two basic options are to set weights to 0 or to randomize them. However, this can result in a vanishing or exploding gradient, which will make it difficult to train the model. To mitigate this problem, you can use a heuristic, a formula tied to the number of neuronators to determine the weights. And a common heuristic used for the hyperbolic tangent activation is called Xavier initialization. Okay. I didn't go deep into the Xavier initialization here, so I think in the future nodes can be added to explain and to introduce these kinds of initialization. So the next step will be the forward propagation. When we use a feedforward neural network to accept an input X from training set and produce an output Y hat, information flows forwards through the network. The input X provides the initial information that then propagates up to the hidden units at each layer and finally produces Y. This is called forward propagation. And actually, we have already covered this part before. And okay, and that is exactly the same thing as we have introduced in this note here. So we will move on to the next step. That is the error function. Objective function is the set of goal towards which the algorithm drives the solution. Often this means to minimizing some error measure on cost function or maximizing some probability function. Because we are dealing with classification and prediction problems, the correct output is known. An error function is defined which captures the delta between the correct output and the actual output of the model. Given the current model weights, we would need minimize the cost function, which is a type of an objective function. So then here comes the gradient descent, a technique. It is a mathematical technique that modifies the parameters of a function to descend from a high value of a function to a low value by looking at the derivatives of the function with respect to each of its parameters and seeing which step via which parameter is the next best step to minimize the function. Applying gradient descent to the error function helps find weights that achieve lower and lower error values, making the model gradually more accurate. And that is what the backpropagation is aimed to do. The objective of backpropagation is to change the weights of the neurons in order to bring the error function to a minimum with the help of gradient descent. Backpropagation calculates how much the final output values are affected by each of the weights. To do this, it calculates partial derivatives going back from the error function to the neuron that carries a specific weight. Backpropagation and gradient descent for neural networks here is a um, point that's worth to dig into and to learn more if you are interested. And uh, the, uh, and if you are interested about the theory behind the backpropagation and how the gradient descent is performed in the neural networks, then um, it is a very interesting and meaningful point for you to uh, dig into the more uh, more deeper theories behind that. So here I will not cover and just move on to the update, wait, and iteratively until convergence. Weights are changed to the optimal values according to the results of the backpropagation algorithms. Since the weights are updated a small delta step at a time, several iterations are required in order for the network to learn. After each iteration, the gradient descent force updates the weights towards less and less global loss function. The amount of iterations needed to converge depends on the learning rate, the network meta-parameters, and the optimization method used. Okay, so I'd like to introduce the learning rate here. Neural network learning rate means how fast the backpropagation algorithm performs gradient descent. A lower learning rate makes the network train faster, but might result in missing the minimum of the loss function. Okay, so that's all for the stages of neural network training part. I will hide the notes here. So next, I will introduce the hyperparameters. A hyperparameter is a setting that affects the structure or operation of the neural network. In real deep learning projects, tuning hyperparameters is the primary way to build a network that provides accurate predictions for a certain problem. So, here is a list of common hyperparameters. First is the hyperparameters related to neural network structure, the number of hidden layers, dropout, activation function, and weight initialization, and the hyperparameters related to training algorithm, the neural network learning rate, deep learning epoch, iterations, and batch size, and optimizer algorithm and neural network momentum. So since some of these hyperparameters we have already introduced, I will not cover them here and just move on to the hyperparameters that we haven't introduced previously. So the first is the number of hidden layers, the depth. So here is the depth and width for neural networks. For a feedforward neural network, the depth of the network is the number of hidden layers plus 1, as the outer layer is also parameterized. The width of the network is the dimensionality of its hidden layers. And the main architectural consideration for designing a neural network are choosing the depth of the network and the width for each layer. And here is a very simple example in the picture with a network with the depth 2 and width 2. So the effect of depth for neural networks. A feedforward network with a single layer is sufficient to represent any function, but the layer may be invisibly large and may fail to learn and generalize correctly. In many circumstances, using deeper models can reduce the number of units required to represent the desired function and can reduce the amount of generalization error. And as is shown in the figure, empirical results show that deeper networks generalize better when used to transcribe multi-digit numbers from photographs of addresses. And as you can see from the graph, the test set accuracy consistently increases with increasing depth. Okay. So the next hyperparameter is dropout. Dropout means what percentage of neurons should be randomly killed during each epoch to prevent overfitting. And the next one would be the deep learning epoch, iterations, and batch size. When you try to train a huge amount of data with limited computer memory, you can separate the whole training set to several batches that can fit into computer memory. Then you feed these batches to your model one by one. After feeding all batches once, you complete one epoch. To successfully train your model, you need multiple epochs. And the last one would be the optimizer algorithms. When a neural network trains, it uses an algorithm to determine the optimal weights for the model, called an optimizer. There are several optimizer algorithms, and such as the stochastic gradient descent, momentum, and Adam. At the moment, there are no. I haven't added notes to explain each of these optimizer algorithms, and I think more nodes can be added for these optimizer algorithms in the future. So we'll just move on to the hyperparameter tuning. Tuning or optimizing hyperparameters involves finding the values of each hyperparameter, which will help the model provide the most accurate predictions. There are 4 methods for hyperparameter tuning. The manual hyperparameter tuning, grid search, random search, and Bayesian optimization. So I will introduce them in the order. So let's start with the manual hyperparameter tuning. Traditionally, hyperparameters were tuned manually by trial and error. This is still commonly done, and experienced operators can guess parameter values that will achieve very high accuracy of deep learning models. However, there is a constant search for better, faster, and more automatic methods to optimize hyperparameters. Grid search is slightly more sophisticated than manual tuning. It involves systematically testing multiple values of each hyperparameter by automatically retraining the model for each value of the parameter. For example, you can perform a grid search for the optimal batch size by automatically training the model for batch sizes between 10 to 100 samples in steps of 20. The model will run 5 times, and the batch size selected will be the one which yields the highest accuracy. And the random search. According to a research study in 2012, testing randomized values of hyperparameters is actually more effective than manual search or grid search. In other words, instead of testing systematically to cover promising areas of the problem space, it is preferable to test random values drawn from the entire problem space. And next is the Bayesian optimization. It is a technique which tries to approximate the trained model with different possible hyperparameter values. To simplify, Bayesian optimization trains the model with different hyperparameter values and observes the function generated for the model by each set of parameter values. It does this over and over again, each time selecting hyperparameter values that are slightly different and can help plot the next relevant segment of the problem space. Similar to sampling methods in statistics, the algorithm ends up with a list of possible hyperparameter value sets and model functions, from which it predicts the optimal function across the entire problem set. And then I will introduce the pros and cons for this method. So for manual hyperparameter tuning, the pros is that it is very simple and effective with skilled operators, and the cons is that it is not scientific, and you will not know if you have fully optimized the hyperparameters. And for grid search, the pros is that it maps out the problem space and provides more opportunity for optimization. And the con is that it can be slow to run for large numbers of hyperparameter values. And next, for random search. According to the study, it provides higher accuracy with less training cycles for problems with high dimensionality, while the con is that the results are unintuitive. Namely, it is difficult to understand why the hyperparameter values were chosen. And last is the Bayesian optimization. The pro is that the original study and practical experience from the industry shows that the method results in significantly higher accuracy compared to random search. And the con is, like random search, the results are not intuitive and difficult to improve on even by trained operators. So that's all for the hyperparameter part. I will hide the notes here. And I think we have done with the deep feedforward networks. We have introduced its goal, its overall structure, the stages of neural network learning, and the hyperparameters. And next, I will move on to two special examples of the neural network. That is the CNN and RNN. And in this video, I will just give a brief introduction of these two kind of neural networks, their applications, and their relationships. And if you are interested in either of these two neural networks, uh, you can work through all the existing nodes here, and I think there are already some nodes to introduce the basic structure of each of the neural networks and how the layers in the neural network are like. So the first is the convolutional neural network, CNN. It is a specialized kind of neural network for processing data that has a non-grid-like topology. Examples include time series data, which can be thought of as a one-dimension grid, taking samples at regular time intervals, and image data, which can be thought of as a two-dimension grid of pixels. The network employs a mathematical operation called convolution. Convolution is a specialized kind of linear operation. Convolutional networks are simply neural networks that use convolution in place of general matrix multiplications in at least one of their layers. So, CNNs can be applied to several applications, including computer vision, like medical image analysis, image recognition and face detection, and also natural language processing, like semantic parsing, sentence modeling, and search query retrieval, and also the drug discovery, like the discovery of chemical features and prediction of medical benefits. Okay, so next would be the recurrent neural network, RNN. Recurrent neural networks are a family of neural networks for processing sequential data. A recurrent neural network is specialized for processing a sequence of inputs x1 to x tau, and each time add additional layers of comprehension on top of the previous inputs. So for the application of RNN, RNNs can be applied to several applications, including temporal analysis, like time series anomaly detection and time series prediction, and also for computer vision, like image description, video tagging, and video analysis, and in NLP, the sentiment analysis, speech recognition, language modeling, machine translation, and text generation. So as you can see that CNN can be used for the grid-like topology, while RNN can be focused on to deal with the problems related to time series and can be used to processing a sequence of the inputs. And also, CNNs and RNNs are not mutually exclusive, as both can perform classification of image and text inputs, creating an opportunity to combine the two network types for increased effectiveness. This is especially true if the input to be classified is visually complex with added temporal characteristics that a CNN alone would be unable to process. Typically, when these two network types are combined, sometimes referred to as a CRNN, inputs are first processed by CNN layers, whose outputs are then fed to RNN layers. CNN long short-term memory architectures are particularly promising as they facilitate analysis of inputs over long periods that can then could be achieved with lower-level RNN architecture types. And currently, these hybrid architectures are being explored for use in applications like video scene labeling, emotion detection, or gesture recognition, video identification, and DNA sequence prediction. Okay, so I think basically that is all the content for the videos, and anyone who are interested in CNN or RNN are welcome to go deep in the from the notes here, and you can explore more more things regarding to the architectures and the layers of each kind of neural network. And so thanks for your time today.